So, here's a wild thought for you. What if a car that is perfectly built, I mean, no broken parts, no bugs in the code, could still cause a terrible accident? It sounds like a paradox, right? But that is the exact problem at the very heart of making self-driving cars safe. Today, we're going to dive into the groundbreaking safety standard that was built to solve this exact puzzle, ISO 21448, or as everyone in the industry calls it, SOTIF. Think about this for a second. Imagine a car where every single component is working flawlessly. The sensors are pristine, the computer is humming along perfectly, everything is exactly as the engineers designed it. Can that car still crash? The answer, incredibly, is yes. And that's the core issue that all the old-school traditional safety standards just couldn't get their arms around. You see, for decades, car safety was all about preventing malfunctions. The old standard, ISO 26262, was totally focused on finding and fixing broken parts, like a faulty brake sensor. But autonomous cars, they're playing a whole different ballgame. They have to deal with the infinite, messy, unpredictable real world. And that's where SOTIF comes in. It tackles those super tricky situations where the car is working perfectly, just as it was designed, but it's still unsafe because it runs into something it was never taught to handle. So here's our roadmap for this explainer. We're going to look at this new kind of danger, break down what we call the 4 areas of safety, see how engineers literally hunt for unknown risks, walk through the intense testing gauntlet these cars go through, and finally ask that huge question: how do we decide what's safe enough? All right, let's kick it off with Section 1, a new kind of danger. So, what in the world is SOTF? Okay, that official definition looks like a mouthful, but the keywords to focus on are functional insufficiencies. Let me give you an example. A car's camera is designed. It's intended to see pedestrians. But what happens if the sun hits it at just the wrong angle, creating a massive glare that blinds it for just a second? The camera isn't broken, but in that critical moment, its functionality is, well, insufficient. SOTIF is the whole science of finding and stamping out these performance gaps before they ever have a chance to cause an accident. Okay, on to Section 2, the 4 areas of safety. I want you to think of this as the safety map that engineers use to make sense of the millions of things that can happen out there on the road. Now, this chart might look a bit technical, but it's actually a brilliant way to break down every possible driving situation into 4 simple boxes. Area 1 is the easy stuff, things we know are safe, like cruising on an empty highway. Area 2 covers the dangers we already know about. The goal there, that V&V stands for verification and validation, is just to prove our safety features work. Area 4 is for things that are unknown but still safe. But the real action, the true frontier, is Area 3. That's the box for unsafe scenarios that we haven't even thought of yet. So here's a classic Area 2 example. A person stepping out onto a dark, unlit road at night. Engineers know for a fact that sensors can have a tough time in these low-light conditions. So the job here isn't to be surprised by it, but to hammer that scenario in testing over and over again, proving that the car's emergency braking works flawlessly every single time. And that brings us to the most fascinating part, Section 3, hunting for unknown risks. This is where engineers basically become detectives, on the hunts for those unknown unknowns hiding out in Area 3. I mean, this is the million-dollar question, isn't it? If you don't even know what you're looking for, how on earth do you find it? You can't just drive millions of miles and hope some bizarre 1 in a billion thing happens. You need a much, much smarter strategy. And this is that strategy. Instead of just endless, aimless driving, SOTIF gets clever. First, in simulations, they throw millions of random combinations of parameters at the system. Think weird sun angles, patches of black ice, things like that. Second, they take normal driving maneuvers, like a lane change and a sudden stop, and combine them in unusual ways to create new events. And third, they use data from real cars on real roads to find those truly bizarre edge cases that you just could never invent in a lab. Engineers also have some incredible tools up their sleeve, like something called search-based software testing. Now, this isn't random at all. It's more like a heat-seeking missile for danger. The algorithms are programmed to actively hunt for the specific worst-case combinations of events that are most likely to break the system. It's like trying to find a needle in a haystack, but you're using a giant, powerful magnet. Okay, so you've found a potential risk. Now what? Well, it enters what we call the virtual to reality gauntlet. This is an intense 3-stage testing process. And the best way to think about it is like a funnel. At the very top, where it's widest, you can run millions, even billions of virtual tests in the software because they're fast and cheap. Then, the most interesting or dangerous scenarios get funneled down to the next stage, and then the next, until only a handful of the most critical tests make it all the way to a physical car on a real test track. And this table just perfectly lays out the trade-offs. Up top, you have software in the loop, or SIL. Its strength is massive scale, but its weakness is the sim-to-real gap. It's not perfect reality. Next is hardware in the loop, HIL. Here you add the car's actual computer into the simulation, which is amazing for testing real-world lag. And finally, you have physical testing. It's 100% real, but it's super expensive and hard to repeat exactly. But when you layer them all together, they create this incredibly powerful defense. Which, of course, brings us to the ultimate question in our final section. After all of this insane, painstaking work, how do you know when you're done? How do you know when a car is actually safe enough for the road? Well, here's the number that many in the industry are shooting for: 10 to the -8 per hour. That means one accident for every 100 million hours of driving. It is an unbelievably high bar to clear, and it's based on the safety record of a very good, very attentive human driver. The goal was never to be just as good as a person. It's to be demonstrably, statistically, way, way better. And that target number doesn't just come out of thin air. It's grounded in these well-established principles for how we accept risk in society. There's ALARP, which basically asks, is the crazy cost of making something a tiny bit safer really worth the benefit? There's GAMAB, which says the new tech has to be at least as good as what it's replacing, in this case, us. And M, which argues the risk from the tech shouldn't be bigger than the other tiny background risks we accept just by living our lives. And that really brings us right to the core philosophy of this entire thing. Building a safe, self-driving car isn't about proving perfection. It's not about creating a flawless machine that can handle every bizarre thing the universe could ever throw at it. It's about a rigorous, intelligent process to find and prove reasonably that you've removed all the unreasonable risks. It's about building a system that we can genuinely, statistically trust. And the real question for all of us going forward is, how will our idea of what's reasonable change as this tech becomes a bigger part of our world?